students. Very good morning. So we are at the last part of equilibrium topic. Okay, I can see less students are there. Lockdown. Okay, so that's what I was telling, that we are in the last part of the equilibrium topic. Right? So any doubts? So in the last class we have discussed about, anyone? We have discussed about pH and calculation. We have discussed about pH and calculation. Then we have discussed about Ka, dissociation constant. Dissociation constant, right? So that is with respect to Ka. That's what we have discussed in the last class. Now, as we know, when it comes to Ka, for pH calculation, what should be knowing? We should know how to see the log. Fine? So that one they can ask, or you can expect in your exams. So when it comes to pH calculation, you should be knowing how to go through the log book. They will provide the log. Fine? So next one is Ka, dissociation constant. Now when it comes to dissociation constant, so what do you mean by dissociation, or what is the relation between strength of an acid and dissociation constant? So dissociation constant is directly related to acid strength. Okay, so what I mean to tell you is, as the value of Ka increases, even acidic strength or strongness of the acid will also increase. Okay, so even we can better word is acid strongness, or strongness of the acid will also increase. Right? So that we have discussed about pKa is equal to minus log of Ka. pKa is equal to minus log of Ka. So based on that, we can tell that pKa value and dissociation constant value, that is Ka value, they are inversely related. They are inversely related. So therefore, as the strongness of the acid increases, pK value should be decreasing. Same as that of the pH. H plus concentration increases, pH value is going to decrease. Same logic is applicable here also. Okay? So as the strongness of the acid will increase, pK value is going to decrease, and vice versa. But when it comes to Ka value, as the strongness of acid is going to increase, even Ka value is going to increase. Fine? Yes, good morning. Good morning everyone. So all of you got the point? So that's where we have the Ka, pKa, and the relation with respect to strongness of the acid, whether a strong acid or a weak acid. That's what we can have information. So based on these values. Fine? So that's what we have discussed in the last class. Then another important equation, what we have discussed here is, that is, what is that? Another important one what we have discussed, that is pH plus POH is equal to 40. Is equal to 40. Now since you people know Ka and all, now we can tell that pKa plus pKb is equal to pKw. Okay, or I can tell that Ka plus Kb is equal to Kw. What is Ka? Dissociation constant of the acid. What is Kb? Dissociation constant of the base. So what is Kw? Ionic product of water. Fine. So that's where we have some of the equations which you have to remember. Now, since last class we were talking about acids, I will continue with that. We have a weak acid like acetic acid or hydrofluoric acid, not hydrogen bromide or hydrogen chloride. I am talking about HF, hydrofluoric acid or acetic acid. All these can be the examples for weak acids. Fine. Say for example, why they are called as weak acid? Because they will not dissociate easily. They will not going to dissociate easily. So therefore they are called as a weak acid. Or with respect to dissociation constant, we can tell that weak acids are those which are having low Ka value or higher pKa value. So weak acids are those which are having lower Ka value or higher pKa value. Got my point? So that's where we have the weak acids. So why? Because they are not going to dissociate easily. So that's where we have the weak acid. Now we will imagine that for the weak acid, initial concentration can be C, and here naturally it will be 0. Initial concentration, it will be 0. Okay. Now after some time there will be some dissociation, right? So by considering degree of dissociation as alpha, degree of dissociation as alpha, so after some time there will be dissociation of acetic acid, right? So there will be dissociation of acetic acid. So with respect to that, we can tell that there is a change in concentration of CH3CO minus and H plus, C alpha, C alpha. So and there will be change in the concentration of C. That means with acetic acid also. So that change can be of minus alpha, C alpha. Got my point? So what I mean to tell you is, here if it is plus C alpha, here it will be minus C alpha, because that much concentration is getting dissociated or decreased. So that much concentration is getting formed due to the dissociation. What is alpha? Degree of dissociation. That will be the change in concentration after the dissociation. Now we will come to what is the concentration at equilibrium. What will be the concentration at equilibrium? So naturally here it will be C minus C alpha. Here it will be C minus C alpha. Okay. So then here it will be C alpha, C alpha. So that will be the concentration at equilibrium. All of you have understood? Any doubts? So what I mean to tell you is, we have acetic acid which is a weak acid. Now initial concentration, like it can be C. So naturally we are talking about initial concentration, product will be 0. Then degree of dissociation, if I consider as alpha, naturally the change in concentration of acetic acid will be minus C alpha. Okay, because that much dissociation is taking place, concentration is going to decrease. Fine. Then here it will be plus C alpha plus C alpha. Now what is the concentration at equilibrium? So naturally whatever amount is getting decreased and initial concentration, we have to deduct the change in concentration from the initial concentration. Then it will be remaining as C alpha, C alpha. All of you have understood? Now based on this, if I want to have the Ka value, so that means I have to talk about CH3 COO minus concentration, then H plus concentration, then CH3 COOH concentration. All of you will agree with me? So naturally it will be C alpha multiplied by C alpha divided by C minus C alpha. Clear? Now further I can write it as C square alpha square C 1 minus alpha. Correct? So C alpha, C square, alpha square, then C minus C alpha, I have taken C as a common factor. So now, one C from here, this C will get cancelled. So that means I am going to get C alpha square 1 minus alpha. That will be the dissociation constant and its relation with the degree of dissociation for a weak acid. For a weak acid. Why we are not talking about strong acid? Anyone? Why we are not discussing about this strong acid? That is because when it comes to strong acid, it will be completely dissociated. So there is no question of undissociated form. So there is no value over here. Everything will be converted into dissociated form. So therefore for strong acid we are not considering. For the weak acid we are considering. So that is Ka is equal to C alpha square 1 minus alpha, and same thing is applicable for the weak base also. So what I mean to tell here is Ka is equal to C alpha square 1 minus alpha, and even Kb is equal to C alpha square 1 minus alpha. Okay, so what is Kb? Kb is nothing but dissociation constant of the weak base. Okay, so they have the same equation. Only unit means naming will be different. There it is Ka and here it is Kb. Any doubts here? Any doubts related to this? So that's where we have the relation between dissociation constant of a weak acid or weak base with the degree of dissociation, where alpha is the degree of dissociation. Whether I am clear? Okay. So in that case, if that is the scenario for the weak acid, now question here is why we have the strong acid and why we have the weak acid. What is the reason? Why some of the acid will behave as a weak acid and why some of them will behave as a strong acid? That will be the question. Okay, so to answer this we have a concept called as, for example, I have acetic acid. Okay, it is a acid, and I have acetate CH3COO minus, which does not have the H plus. They are the acceptor of the H plus. This can be the acceptor of the H plus. So what I mean to tell you is, this will donate the H plus. So therefore it has become CH3CO minus. CH3CO minus can take up the H plus to become the acid. So therefore these two species differs from each other by one H plus. By one H plus. So therefore it is called as conjugate base. Therefore it is called as conjugate base. So try to understand this. So what I mean to tell you is, acetic acid is the conjugate acid of the acetate conjugate base, or I can tell that acetate is the conjugate base of the acetic acid, or acetic acid is the conjugate acid of the acetate. All of you have understood? So that's where I have got the acetic acid, and that's where I have got the acetate. So why I am discussing this one? Because I want to give the answer that why acetic acid is a weak acid. Why not it can be behave as a strong acid? To answer that I am going with this particular concept. So now what do you mean by conjugate base? Okay, what do you mean by why acetate is called as a conjugate base? Because they differ from the acetic acid by 1 H plus. Okay, so whenever acetic acid is going to release the H plus, it will become the acetate. And acetate can accept the H plus. That means it is the behavior of the base. So therefore it is called as conjugate base. Clear? Any doubts? Any doubts with regard to this one? Try to understand it properly. Now, based on this information, that is acid and its conjugate base concept. So based on its information, now I can tell that, listen to me carefully, now I can tell that acetic acid is a weak acid. Acetic acid is a weak acid because its conjugate base is a strong base. Clear? Acetic acid is a weak acid because its conjugate base, that is acetate ion, is a strong base. Fine? So that's what I can tell here. Because conjugate base, in this case which one it is? Acetate. Conjugate base is a strong base. Since conjugate base is a strong base, it will not going to release the H plus easily. It will hold the H plus with it. So due to that, acetic acid will not donate the H plus easily. Because acetate will not allow or it will not release the H plus, it will hold it back. So therefore we are giving the statement as conjugate base, acetate is a strong base. Due to that, acetic acid is a weak acid. Whether I am clear? Fine. Now same if I extend it to any of the strong acid. Any doubts here? No doubts? Okay. Now if I want to extend it to a strong acid, any of the strong acid I can take. That can be, okay. Then that can be, I will take the example of sulfuric acid, which will be dissociated as H plus, then HSO4 minus. This is a bisulfate ion. Okay. Now I can tell that sulfuric acid and bisulfate, they are the conjugate acid and conjugate base of each other. Okay, I can tell that bisulfate is the conjugate base of the sulfuric acid, H2SO4. Right. Now why sulfuric acid is a strong acid? Because its conjugate base, bisulfate, is a weak base. It will not take up the H plus easily. Instead of that, it will release the H plus easily. So therefore, conjugate base is a weak base. Due to that, sulfuric acid is behaving as a strong acid. Got my point? Another example for conjugate base and its acid. Fine? So, acid can behave as a strong acid or weak acid based on its conjugate base. And same thing is applicable for the bases. A base can behave as a strong base or a weak base depending on its conjugate acid. Okay now? Any doubts? Fine? Right. Very interesting point here is, sir, in case of HCl, since chloride conjugate base is weak, so it is the reason why I say, yes Ashish. Since chloride Cl minus will be happy, it's a octet state, so it will not take up the H plus. So therefore Cl minus, since it is a weak conjugate base, therefore HCl is a strong acid. There are many other factors in which solvent we have taken and all, but that one we are not going to consider here. Fine? So that's where we have the reasons. Fine? So now another interesting point here is, as we have discussed in Lee-Chatler's principle, here if I add the H plus from outside or acetate ion from outside, what do you think with respect to the dissociation? What do you think? So what I mean to tell you is, when I will add the H plus from outside, what will happen? Then I can tell that CH3 COOH. So CH3 COO minus H plus. That means I am adding the H plus from outside. So what is happening? Can any one of you tell me whether acetic acid dissociation is much more reduced? Yes or no? Dissociation of acetic acid is much more reduced. I will add H plus from outside or acetate ion from the outside. What will happen? Dissociation of acetic acid will be reduced. Yes, Ashish, it will be reduced, no doubt. Dissociation of acetic acid will be reduced, or I can tell that reaction will be shifted towards the left hand direction. Right? So yes, it will be shifted towards the left hand direction. So that's what the Lee-Chatler's principle talks about. Right? So yes, all of you are right. So reaction will be shifted towards the left side. Fine? So that means, since we are dealing with the ions over here, same thing we have studied with respect to factors affecting the equilibrium, where one of the factor is concentration. That's what I told during that time, that if you add any of the product, reaction will be leftward. If you add any of the extra reactants, reaction will be forward. Same logic is applicable here also. But the only thing here is, since we are talking about ions, since we are adding the ions, this condition is called as common ion effect. This condition is called as common ion effect. So what do you mean by common ion effect? So common ion effect means by adding the ions which are already present in the solution. That means acetate and H plus, already they were present in the solution. So by adding the extra ions which are already present in the solution, reaction will be drifted or shifted towards the other direction. That is called as common ion effect. So that one we will call it as common ion effect. Fine? All of you have understood? Any doubts? Any doubts related to common ion effect and all? No doubts, right? So all of you have understood conjugate base and its acid concept. Then all of you have understood common ion effect. Okay? So in that case, we will move to the next one. We will move to the next one, that is salts. Salts, okay? So we have not discussed about salts. Now, all of us we know that salts will be having two ions together. One is a cation and one is an anion, right? So that's where we have the salt. Now, how this salt will be formed? Naturally, when an acid and when a base, they are going to interact with each other, then due to the neutralization reaction, there will be formation of a salt. NaCl is the example. But NaCl is the only salt in the nature? No, there can be anything. For example, if I take acetic acid, okay, I will treat with the sodium hydroxide, a strong base. So due to that, there will be formation of sodium acetate plus water. Sodium acetate plus water. So therefore, this is nothing but sodium acetate. Another example for the salt. This is also an example for the salt. Same way, if I take sulfuric acid, if I treat with the sodium hydroxide, so naturally there will be liberation of water, and along with that there will be formation of sodium sulfate. Sodium sulfate. So another example for the salt. So sodium chloride, sodium acetate, sodium sulfate, all of them, they are the examples for the salt. Okay, all of you have understood? So naturally, when they are mixed with water, they will dissociate it as Na plus Cl minus. Same thing for sodium acetate also, they will dissociate it as acetate and Na plus. Same thing for sodium sulfate, 2Na plus and SO4 minus 2. So they will be dissociated. Most of the salt, when it is added, solubility may vary depending on the salt, but in general we can tell that these salt, they will be having cations and anions together. So therefore when they are added to the water, they will dissociate as respective cations and anions. Fine. So that's where we have the salts. Any doubts with regard to this one? All of you have understood, right? So that's where we have the salt. However, one point you should remember that whatever reaction just now I have told, so based on that we can clearly see that NaCl is a salt resulted by the mixing of strong acid and strong base. Strong acid and strong base. Try to understand it carefully. Sodium chloride is resulted by the mixing of strong acid and weak base. Strong base. All of you will understand? All of you have understood? So why strong acid? Because HCl. Why strong base? Because sodium hydroxide. So that's where we have got the NaCl. However, all of you know that why HCl is a strong acid. Why HCl is a strong acid? Because its conjugate base, chloride, is a weak base. Its conjugate base, chloride, is a weak base. So why sodium hydroxide is a strong base? Why sodium hydroxide is a strong base? That is because its conjugate acid, that is Na plus, its conjugate acid, that is Na plus, is a weak acid. It's a weak acid. So what I mean to tell here is, sodium chloride is having Na plus, which is a weak conjugate acid of the strong base, that is sodium hydroxide, and it is having Cl minus, which is a weak conjugate base of the acid HCl. So therefore, when I will add it to the water, listen to me carefully, when I will add it to the water, the solution will remain neutral, or I can tell that no change in pH. No change in pH. Why there is no change in pH? Because Na plus will not take up the OH minus, or Cl minus is not going to take up the H plus. Got my point? So what I mean to tell you is, we have Na plus, okay, OH minus, since water is neutral, then we have the Cl minus and H plus. So it is not going to take up the OH minus, it's not going to take up the H plus. So due to that, what will happen? Whatever H plus OH minus concentration will be there, it will not be disturbed. So naturally pH will remain same. Okay, I have a glass of water. When you add a pinch of sodium chloride, So nothing will happen to pH of that particular water due to this reason. All of you have understood? Any doubts? Okay. So ಹಾಗಾದ್ರೆ I will take another salt. I will take another salt, that is sodium acetate. That is nothing but sodium acetate. CH3COONA. Sodium acetate. ಹಾಗಾದ್ರೆ how this sodium acetate has been formed? By mixing the weak acid with strong base. Weak acid with strong base. So which was that weak acid? That weak acid was acetic acid. Which is that strong base? That strong base was sodium hydroxide. Right? So what I mean to tell you is, why acetic acid is a weak acid? Because its conjugate base, acetate ion, is a strong base. So that means we have this strong base here. Why sodium hydroxide is a strong base? Because it is having a weak conjugate acid, that is Na+. Fine? Now can you tell me, if I add a small amount of, or if I add sodium acetate to the water, what will happen to the pH of the water? Whether it will change or it will not change? Just tell me that one, whether it will change or it will not be changed. If I add sodium acetate to the water, you tell me whether pH will change or not. Yes or no, that's all. When I am adding NaCl, no change in the pH. It will change. Okay. So Ullas is telling no change in the pH. So we will observe. For example, I have acetate. Okay. If it has to take up, it has to take up the H+. I have the Na+. If it has to take up, it has to take up the OH-. Okay. So why sodium hydroxide is a strong base? Because it will release the OH- very easily. So that means Na+ is not going to take up the OH-. Why acetic acid is a weak acid? Because acetate is not going to release the H+. That means it will take up the H+. It is going to take up the H+. So therefore, what is happening? OH- level is increasing, H+ level is decreasing. So naturally pH is going to increase. pH will increase because decrease in the concentration of H+. Decrease in the concentration of H+. pH will increase. Fine? All of you have understood? Any doubts with regard to this one? So depending on the salt, therefore depending on the salt, they are going to change with respect to pH of the solution. All of you have understood? So that's where we have the condition. Any doubts? If I take another salt, which I have not discussed here, if I take another salt, so that is which was prepared by mixing the ammonium hydroxide with HCl. Naturally, I am going to have the water and ammonium chloride. Water and ammonium chloride. Ammonium chloride is a salt now. Right? Now, when I will take ammonium chloride, how it has been prepared? It has been prepared by taking the weak base. Ammonium hydroxide is a weak base and strong acid. However, why ammonium hydroxide is a weak base? Because a strong conjugate acid. Strong conjugate acid, that is ammonia. Okay, so why Sl is a strong acid? Because it is having a weak conjugate base, that is chloride. So naturally I have two ions, ammonium, and I have another ion as Cl minus. So there is OH minus and there is H plus. So Cl minus is not going to take up the H plus because Cl minus is not going to take up the H plus because why do not take up the H plus? Why do not take up the H plus? Because it's a weak conjugate base. But ammonia will take up the OH minus because it's a strong conjugate acid. So due to that, what will happen? OH minus will going to decrease, but H plus is going to increase. Exactly opposite. So therefore, whenever ammonium chloride is added to the water, whenever ammonium chloride is added to water, what will happen to the pH? pH is going to decrease. pH is going to decrease. So that's where we have the salts. So depending on the nature of the salt, pH of the resulting solution is going to be changed. Any doubts? Any doubts with regard to these things? All of you have understood? So that's where we have the salts. Then we will come to the last part. We'll come to the last part, that is buffers. Buffers anta ಹೇಳ್ಬಿಟ್ಟಿರಾ? That is buffers. Okay na? So ಹಾಗಾದ್ರೆ what are buffers? Definition they may ask. And all of us we know that buffers are those solutions. They are those solutions which will resist the change in pH. Which will resist the change in pH. Right? So that's where we have the definition for the buffers. So buffers are nothing but a solution which is going to resist the change in pH. What is that in these buffers? Why they are going to, how come they are going to resist the change in pH? So what I mean to tell you is, I have a buffer solution. Okay? So I have a buffer solutions here. Now the pH might be somewhere around 7. We'll imagine pH might be somewhere around 7. Now I am adding H plus from outside. Small amount, not in liters. Okay, na? So small amount of H plus will be added from outside, but there is no change in the pH. It will remain as 7 only. Now I am going to add some amount of OH minus from outside, but still pH will remain as 7. There is no change in the pH. So pH 7 I have taken as the example. Buffers can be slightly acidic pH, neutral pH, or alkaline pH. We have different varieties of buffers. So depending on the requirement, we will utilize the respective buffers. Fine. So how come these buffers they are resisting the change in pH? Because these buffers will be made up of, for example, I will take one of the example as acetate buffer. We have got the acetate buffer. So acetate buffer is prepared by mixing acetic acid with sodium acetate. Acetate buffer will be prepared by mixing acetic acid and sodium acetate. So naturally, when I have the solution of this one, we'll imagine this is the container where we have taken the acetate buffer solution. So naturally, I will be having a reaction where small amount of acetate will be released and there will be small amount of H plus and there will be CH3COO minus and Na plus. So these are the composition of this acetate buffer solution. So what and all it will be there? Small amount of acetate due to the acetic acid, very small amount. Then small amount of H plus will be there, and acetate ions will be there due to the sodium acetate dissociation, and Na plus will be there. That will be the composition present in the solution, acetate buffer solution. Now when I am going to add the H plus from the outside, now what will happen? Whatever acetate ions are there, all of us we know acetate is a strong conjugate base. So it will be taken up by the acetate ion and it will get converted into acetic acid. So what is happening? So that means there is no change in the pH, because whatever H plus we are adding, it's getting taken up by the acetate ion, which is a strong conjugate base of acetic acid. So from where this acetate ion came, that is because of the small amount of dissociation of acetic acid and then the dissociation of the sodium acetate, which is a salt, which will be dissociated in the water. That's what I told. Okay, so therefore there is no change in the pH, although we have added the H plus from outside. Fine. Now what will happen if I add the OH minus? What will happen if I add the OH minus? So naturally, whatever H plus is getting released, it will be neutralizing this OH minus. Along with that, since H plus outside it is getting decreased, it will make more acetic acid to get dissociated. Listen to me carefully. Since H plus is getting consumed by the added OH minus, so therefore more acetic acid will be dissociated, because common ion effect is exactly opposite to this. Common ion effect is getting nullified. We are removing the H plus. So more acetic acid will be dissociated. Okay? So therefore, once again, there is no change in the pH, although we have added the OH minus. So due to that, in general, we can tell that buffers are made up of weak acid and its salt, or to be more appropriate, we can tell that it is made up of weak acid and its conjugate base. And its conjugate base. So that's where we have the buffers. Okay? So you can give the definition of any two. Either you can tell it's a solution which will resist the change in pH, or you can tell that they are prepared by, or they are the solution of weak acid and that salt. Anything is fine. This can be more appropriate, no doubt, which will resist the change in pH. Any doubts? Okay. If you are not having any doubts, by this we have finished the equilibrium. Before closing this session, we will solve one problem. We will solve one problem. Okay, na? Sir, from this chapter, which concepts are deleted? So that deleted one is Hasselbalch equation, that is next to the buffers. Then they have deleted solubility product and all. They have removed those things. Very small amount has been deleted because it is a important basic chapters which will be required for further studies. Okay, so therefore those things I have not discussed. Henderson-Hasselbalch equation and solubility product and all. And whatever I have discussed, everything will be there. It is there in your syllabus. Okay, na? Okay. So if that is the case, take down the problem. Ionization constant of ionization constant for hydrofluoric acid is 3.2 into 10 to the power of minus 4. 3.2 into 10 to the power of minus 4. Okay? If 0.02 molar hydrogen fluoride is taken, calculate the degree of dissociation. Degree of dissociation. Degree of dissociation of the same. Degree of dissociation of the same. Okay, na? Degree of dissociation of the same or for the same. Anything is fine. Okay, we have to calculate the degree of dissociation. Now, it can be extended further that after finding the degree of dissociation, even you can find out the concentration, then even we can find out the pH of that particular solution. That one we are going to discuss. But before that, we have to find out the degree of dissociation, that is alpha value. All of you have understood? We have to calculate the alpha value. So, same as that of the weak acid, because hydrogen fluoride is a weak acid. So, same as that of the degree of dissociation for weak acid, even here also we have to do the same thing. That is, we have got the hydrogen fluoride. When it is added to the water, it will be dissociated as H3O plus, since I have taken the water, otherwise I can mention it as H plus. Anything is fine. So otherwise I can mention it as H plus. So this is the reaction. Okay. Now, first I will write the initial concentration. Sorry. First I will write the initial concentration. What is that? 0.02 molar. They have given, right? So they have given it as 0.02 molar. That will be the initial concentration. What will be the concentration of these two? 0. Water we are not considering because it is a liquid. Okay, we are not going to consider that one. Now we have to find out what is the change in concentration by considering alpha as degree of dissociation. Alpha as degree of dissociation. What is that change in the concentration? Here it will be 0.02 alpha, 0.02 alpha, and here it will be minus 0.02 alpha. So whatever earlier we have discussed, it was a general one, where we used to take it as C alpha, where C is the concentration. Okay, so that concentration here it is 0.02. Okay, now concentration at equilibrium. So naturally it will be 0.02 initial concentration minus 0.02 alpha. Right? And here it will be 0.02 alpha, 0.02 alpha. Correct? That will be the concentration at equilibrium. Now we can write Ka is equal to H3O plus concentration, then fluoride concentration divided by hydrogen fluoride concentration. Water we are not going to consider, it is a liquid. So H3O plus is 0.02 alpha multiplied by 0.02 alpha divided by 0.02 minus 0.02 alpha. All of you got the point? Any doubts up to here? Now what I can write here is 0.02 alpha multiplied by 0.02 alpha divided by 0.02 1 minus alpha. I have taken 0.02 as the common in the denominator. So 0.02, 0.02 will get cancelled. So therefore I can write it as 0.02 alpha square divided by 1 minus alpha. All of you got the point? Any doubts up to here? Any doubts? All of you have written? So 0.02 alpha square divided by 1 minus alpha. Okay. So I will remove this. Even this one I will remove. I will keep only the last one. Okay. So they have given the Ka value. What is that Ka value? Ka value is 3.2 into 10 to the power of minus 4. So therefore 3.2 into 10 to the power of minus 4 is equal to 0.02 alpha square divided by 1 minus alpha. Or I can tell that, so therefore 3.2 into 10 to the power of minus 4 divided by 0.02 is equal to alpha square 1 minus alpha. Correct? So now 3.2 divided by 0.02, how much it will be? 3.2 divided by 0.02, how much it will be? It will be somewhere around 160. 3.2 divided by 0.02. Anyone is doing that one? 3.2 divided by 0.02. Yeah, it will be 160. So we can mention it as 160 into 10 to the power of minus 4 is equal to alpha square divided by 1 minus alpha. So I will keep it, I will try to convert it into quadratic equation. So 160 into 10 to the power of minus 4 into 1 minus alpha is equal to alpha square. Correct? Is equal to alpha square. So based on that, I can tell that 160 into 10 to the power of minus 4, that is multiplied by 1, minus 160 into 10 to the power of minus 4 alpha is equal to alpha square. Is equal to alpha square. Correct? Now very important point what we can do here is, we can make it this one as, 1 minute. Yeah, it's correct. So we can make that 160 as a reduced value, because otherwise it will be very difficult to calculate. We can reduce the values. Otherwise it will be very difficult to calculate. Okay na? So therefore what we can do is, we can go with 1.6 into 10 to the power of minus 2 minus 1.6 into 10 to the power of minus 2 alpha is equal to alpha square. Or even you can make 0.16, anything is fine. Anything is fine. All of you have understood? So this is what we have got. Now further I will convert where alpha square plus, I will take this on the other side, 1.6 into 10 to the power of minus 2 alpha. This one is also on the other side. Then it will become 1 minus 1.6 into 10 to the power of minus 2 is equal to 0. Correct? So this one also I have taken it on the other side, it will become plus. This one also I have taken it on the other side, it will become minus. Correct? Only thing is I want to keep alpha square in positive form. That's all. So based on this, I can tell that A is equal to 1, B is equal to 1.6 into 10 to the power of minus 2, and C is equal to minus 1.6 into 10 to the power of minus 2. Now use the quadratic equation and solve. Tell me the value of alpha. Alpha is equal to minus b plus or minus square root of b square minus 4ac divided by 2a. This is the quadratic equation what we have. Substitute these values and tell me the alpha value. Substitute these values over there. Tell me the alpha value. Two values we should get. And please remember that, like earlier in class we have discussed about similar type of problem using quadratic equation. There we got both the values as positive because we have got the minus b value. But here b value is positive. So you should get one negative and one positive value. All of you are doing? Can anyone send me the answer? So if you solve it further, alpha value can be 0.12 or minus 0.12. Alpha value can be positive 0.12 or negative 0.12. Okay? Now naturally which value we should take? Positive value we should take, not the negative value. Because there is a degree of dissociation. So therefore alpha value should be positive, not the negative. So therefore you should write that one. By selecting the positive value, alpha will be equal to 0.12. Alpha will be equal to 0.12. Fine? All of you have understood? So alpha value we have identified. Now whether we can calculate the concentration of all these things, all the molecules at equilibrium, naturally we can calculate easily. For example, if I take H3O plus, which will be equal to fluoride concentration, which will be 0.02 into 0.12. How much it will be? 0.02 into 0.12. So that will be somewhere around 0.0024 molar. Don't forget to write the unit. Molar. Okay? Same way, when I am talking about hydrogen fluoride concentration, when I am talking about hydrogen fluoride, don't talk about water. Water we are not considering. So it will be 0.02, right? That means C into 1 minus alpha, right? So C is 0.02, 1 minus 0.12. What will be the value? It will be 0.0176 molar. That will be the concentration. That will be the concentration, 0.0176 molar. Any doubts? So products will be 0.0024 molar, reactant will be 0.0176 molar. Fine. Even we can find out the pH also. So what we have to do for the pH calculation? We have to take the value of 0.0024 because that is the H plus concentration. So therefore pH is equal to minus log of H plus concentration, that is nothing but minus log of, so 0.0024, I will write it as 2.4 into 10 to the power of minus 3. 2.4 into 10 to the power of minus 3. So that means it will be put to minus log of 2.4 plus minus 3 log of 10. Okay, yesterday we have discussed, right? So naturally the answer will be 2.62. The answer will be 2.62. Therefore the pH will be 2.62. Fine. Any doubts with regard to this one? So this is where for competitive exams you can expect the questions from this part. Okay na? So pH they have asked even for board exam also, but rest of the things I am talking about. Any doubts? By this we have finished the equilibrium chapter completely. All of you have written this one. Shall I remove? Okay. So this is where we have the degree of dissociation calculation. Then by finding the degree of dissociation alpha value, we have calculated the concentration of all the molecules involved in that reaction. Then we can calculate the pH also because we have got the H plus concentration. So by this we will conclude the session. Thank you. Thank you very much and all the best. Do well in your exams. Fine. Take care. Bye.